Welcome to this lecture on the fundamentals of biomolecules. Today, we're going to explore a fascinating phenomenon known as the mutarotation of glucose. When you dissolve sugar in water, you might think the molecules just float there, unchanging. But in reality, they are performing a continuous, dynamic dance, constantly shifting their shapes. Understanding this hidden balancing act is absolutely crucial, not just for passing your chemistry exams, but for understanding how life itself processes energy. Let us dive in and uncover what mutarotation really means. To build our intuition, imagine you have a special type of folding chair that can lock into two different shapes, one leaning forward and one leaning backward. If you place this chair in a magical room, it does not just stay in one shape. It constantly unfolds, straightens out for a split second, and then folds into the other shape. Over time, if you had 100 of these chairs, you would notice they eventually settle into a steady, predictable mix. This is exactly what happens to a molecule of glucose when you dissolve it in a glass of water. It does not stay frozen in one shape, but rather constantly opens up and snaps back into two slightly different ring shapes until it reaches a perfect, stable balance. Now that we have a mental picture, let us look at the formal scientific definition. In scientific terms, mutarotation is defined as the gradual change in the specific optical rotation of a freshly prepared solution of a chiral substance until it reaches a final equilibrium value. When you first dissolve a specific form of glucose in water, it bends polarized light at a very specific angle. But as the molecules begin their dynamic dance, flipping back and forth between shapes, the overall light-bending property of the solution slowly changes. The rotation literally mutates over time. This continuous shift in optical properties is the physical evidence that the molecules are rearranging themselves, and it only stops when the system achieves a final, stable equilibrium. This brings us to the actual chemical structures involved in this process. In its solid state, sugar exists primarily in one specific, locked ring structure. For glucose, this ring can take one of two forms, which we call the alpha anomer or the beta anomer. You can think of them as the two locked positions of our folding chair. Because these two anomers have slightly different three-dimensional geometries, they interact with light differently. Specifically, they bend polarized light at completely different angles. If you have a jar of pure alpha glucose and a jar of pure beta glucose, they will look identical to the naked eye, but a polarimeter will immediately reveal their distinct optical signatures. So, how exactly does one anomer turn into the other? When you dissolve this solid glucose in water, the rigid ring structure temporarily breaks open. This forms what we call a straight-chain aldehyde intermediate. This straight chain is the equivalent of our folding chair straightening out for a split second. It is highly unstable and cannot stay in this open form for long. It immediately closes back up into a ring. However, when it closes, it has a choice. It can close in two different ways to form either the alpha anomer or the beta anomer. This constant opening and closing is the fundamental mechanism driving mutarotation. Before we move on to the mathematics, let us understand why this matters in the real world. Understanding mutarotation is incredibly important in both medical diagnostics and the food industry. In our bodies, enzymes are highly specific. They often only recognize one specific anomer of glucose to carry out vital metabolic reactions. If glucose could not undergo mutarotation to switch between these forms, our cells might literally starve because the enzymes would not be able to process the incorrect shape of the sugar. Furthermore, in the food and beverage industry, The sweetness and crystallization properties of syrups depend heavily on the exact ratio of these sugar shapes. Without mutarotation, a freshly made sugar syrup would behave in completely unpredictable ways. Now that we understand the concept, let us look at how we measure it mathematically. This formula calculates the specific optical rotation, which is the standard way we measure how much a sugar solution bends light. Let us break down the symbols. The term on the left is the specific rotation, which is a constant characteristic of the molecule at a specific temperature and light wavelength. On the right, the numerator is the actual observed angle of rotation that we read directly from the instrument, in degrees. In the denominator, we have the concentration of the glucose solution in grams per milliliter multiplied by the length of the sample tube in decimeters. If you increase the concentration, or the tube length, the observed rotation will increase because the light passes through more sugar molecules, but the specific rotation itself remains perfectly constant. This brings us to our second important equation. This formula allows us to calculate the final specific rotation of the glucose solution once it has reached perfect equilibrium. Conceptually, this is just a weighted average of the two anomers present in the water. The term on the left is the final stable specific rotation of the mixture. On the right, we multiply the fractional percentage of the alpha anomer by its pure specific rotation and add it to the fractional percentage of the beta anomer multiplied by its pure specific rotation. The open chain form is ignored because it is present in a tiny negligible amount. Physically, if the fraction of the alpha anomer increases in the solution, the final equilibrium rotation will shift closer to the pure alpha value. Let us see this formula in action with a concrete example. We are asked to determine the final specific rotation of a D-glucose solution at equilibrium. We are given the pure specific rotations, positive 112.2 degrees for alpha and positive 18.7 degrees for beta. The equilibrium mixture is 36% alpha and 64% beta. First, we must convert these percentages into decimal fractions by dividing by 100, giving us 0.36 and 0.64. Working with decimal fractions is essential for weighted averages. Next, we substitute these values into our equilibrium formula. We multiply the alpha fraction by its specific rotation and the beta fraction by its specific rotation. Adding these contributions together gives us a final equilibrium specific rotation of positive 52.36 degrees. This physical result tells us that any glucose solution will always settle at this exact light bending angle. Now that we have calculated the equilibrium specific rotation, let us use it in a laboratory scenario. A student has a glucose solution at equilibrium, so the specific rotation is positive 52.36 degrees. The concentration is 0.1 grams per milliliter, and the polarimeter tube is 2 decimeters long. We need to find the actual observed angle on the instrument. We start with our standard specific rotation formula. However, since we want to find the observed rotation, we must use basic algebra to rearrange the equation. By multiplying both sides by concentration and path length, we isolate the observed rotation. Now we simply plug in our numbers. 52.36 multiplied by 0.1 multiplied by 2. The units cancel out perfectly, leaving us with positive 10.472 degrees. This means the light beam is physically twisted by about 10.5 degrees to the right. Let us visualize everything we have learned so far in this diagram. On the left, you see the ring structure of the alpha anomer, which contributes a high rotation of positive 112.2 degrees. On the right is the beta anomer, with a lower rotation of positive 18.7 degrees. Notice the straight chain intermediate in the very center. The bold, double-headed arrows connecting them are crucial. They represent the dynamic, continuous opening and closing of the rings. The percentages show that the beta form is slightly more favored, making up 64% of the mixture. Finally, at the bottom, we see the result of this dynamic balancing act. The equilibrium mixture settles exactly at positive 52.36 degrees. This diagram beautifully captures the moving reality of biological systems. We have covered a lot of ground today, so let us summarize the key takeaways. First, mutarotation is the fascinating process where a single type of sugar molecule constantly opens and closes to switch between two different ring shapes in solution. Second, for glucose, this means the alpha and beta anomers continuously interconvert through a highly unstable open chain intermediate. Third, this dynamic balancing act is physically observed as a gradual change in optical rotation, ultimately settling at a constant equilibrium value of positive 52.36 degrees. Finally, remember that this is not just abstract chemistry. It is a vital process that allows our enzymes to function and dictates the properties of the foods we eat. You now have a solid understanding of the dynamic reality of biomolecules.